Hey guys, so I have an interesting problem here that I saw in a machine learning class where we are supposed to compute PCA by hand. So let's take a look. It says consider this sample of 6 points. Each point is an x sub I in R2. And here are points here. And the first task is to compute the mean of the sample points and write the center design matrix x dot. Okay, so taking the mean is pretty straightforward. I guess I'll call the mean x bar for now. And so the mean of the 6 points, right, we're taking just a typical mean. So we're going to have to divide by 6. And we want to really just sum up each x sub I from 1 to 6. And, we'll just call it from left to right, 1 through 6, right? And so this will end up being 1 over 6 times, let's see. So for the first element here, we have 0 plus 0 plus 1 plus 1 is 2 plus 2 is 4 plus 2 is 6. So for the first, you can think of them, if this is machine learning, right, you can think of these as like features for each sample point or whatever. And then the second feature kind of sum would be 0 plus 1 is 1 plus 0 is 1 still, plus 2 is 3 plus, well, there's another 3 there, so we're going to get a 6 again. And so we see that the mean is 1, 1. And now we need to make a centered design matrix. So a centered matrix just is a matrix where you've subtracted the mean from each point. Design matrix, right, you take all of your points, and you just put them together in a matrix. And again, I'm going to consider each one of these elements as it's like a feature. So we could say our x dot matrix will be like this. So we want to subtract the mean from each data point, right? So we have 0, 0. If we subtract the mean, we're going to actually get negative 1, negative 1. For the next point, we'll get negative 1, 0, and then we'll get 0, negative 1 for, call it x3. Then we'll get 0, 1 for x4. We will get 1, 0 for x5, and then 1, 1 for x6. Okay, so there's our center design matrix. Let's move to the next part of the problem. It says find all the principal components of this sample and then write them as unit vectors. Okay, so move this up, give ourselves a little more room. We're going to need it. I think a big part of doing this problem hinges on whether or not you remember this key fact that the principal components are actually related to the eigenvalues of this matrix here, right? So x dot transpose x dot. And so we want to compute that first so that we can get the eigenvalues and then we can get the eigenvectors. And then we'll convert them to unit vectors, right? Okay. So to get our new matrix here, and it's going to be, notice a symmetric matrix, right? First thing we want to do is essentially take the dot product of this vector with itself, right? And so we could just kind of look here and just think of like, square this, square all the elements and sum them up for the first row, essentially, right? It's negative 1 squared is 1, negative 1 squared is 1 again, so their sum is 2. We've got 2 zeros, square those, get nothing, so it's still 2. And then we square each one of those. Again, we're going to sum them, we get 2. We add it with those 2, we get a 4. Okay, and then we need, let's get an off diagonal. So we're going to do this row with that column, or if you want to just think about it, just take the dot product between these two rows, to be honest. So we could just think about it that way, right? So that is 1 when you take the product, 0, 0, 0, 0. So these 4 elements here, their products are 0, so they don't contribute. So you got 1 plus 1 times 1 is 1, so 2. And this element here is going to have the same exact dot product. That's also 2. And then finally, we essentially just need to take the dot product of this guy with itself. And so what do we got? We got that'll give you 1, so you square it, right? So 1 plus 0 plus 1 again is 2, plus 1 is 3, plus 0 plus 1 again is 4. Okay. And so there's our matrix, x dot transpose x dot. And again, we need to find the eigenvalues and eigenvectors of this matrix so that we can get our principal components. You, of course, can find your eigenvalues doing the typical, find your characteristic equation, right, by subtracting the, lambda. And that's all good and well. I like to, when I have a 2 by 2, just take advantage of the fact that the trace of our matrix, x dot transpose x dot, has to be equal to lambda 1 plus lambda 2. And the determinant of our matrix has to be equal to the product of our eigenvalues. Okay, so what's the trace? Well, if you recall, the trace is just the sum of the diagonal elements, so we have 8. And the determinant, right, so we have to do 4 times 4 is 16 minus 4, so we get 12. So we need two numbers that multiply to 12 and add to 8. That's actually 2 and 6. So we usually want to make the larger eigenvalue, the one in the first position. So I'm going to go ahead and call lambda 1 6, and lambda 2 will be 2. Okay, next, find the eigenvectors associated with the eigenvalues. So just as a brief reminder that basically when you have, some matrix A, you do A minus lambda I times X equals 0. And, those X values, those X vectors rather, that make this 0 are your eigenvectors. Another way to think about it is just think about they are the vectors which are in the null space of A minus lambda I. Or in our case specifically, it's going to be, our eigenvectors are going to be the null space of x dot transpose x dot minus lambda, let's just say sub I, times I. So we'll have, in our case, 2 eigenvectors, of course. They need to be in the null space of that matrix. So what we could do is let's do the first eigenvector, which we're just going to call v1. And so here we take our initial x dot transpose x dot, and let's subtract out the first eigenvalue from the diagonal elements. So we've got 4's here. We're going to subtract 6, giving us the matrix negative 2, 2, 2, negative 2. And so you can just eyeball it, right? And you can see that if you wanted to, I guess I call them V1 and V2, or, I don't know. I'm calling the whole vector V1, or yeah, V1. So I'm just going to call this X and Y for now, right? So essentially you're taking a combination of the columns to get 0, 0, and you can see the good combination here is just column 1 plus column 2, right? Because these are opposites here, they'll add to 0. And so this tells us right here that V1, which is kind of our eigenvector 1 here for the associated with the first eigenvalue, is just 1, 1. But we were asked to find unit vectors to make these unit vectors. And so to make it a unit vector, you just need to divide the vector elements by the length of the vector, and you can fairly easily see the length of this vector, right, is the square root of 1 squared plus 1 squared, or in other words, the square root of 2. So I'm going to call the unit vectors versions of the eigenvectors u, so I'll call it u1, and u1 will just be equal to 1 over root 2, 1 over root 2. Okay. Let's find the second eigenvector. The second eigenvector will be associated with lambda 2 equals 2. So let's move up to some clear real estate here. You can see the other problems waiting for us. Real quick, our matrix becomes, when we subtract the second eigenvalue rather, it was 4, 2, 2, 4. Well, when you subtract 2 from the diagonal, you're going to get 2, 2, 2, 2. So here, I'm not going to go through everything I did last time. You can just easily see what is the right vector to take the combination of these columns to give you 0. Well, we'll call it v2, and that will be 1, negative 1, or negative 1, 1. Doesn't really matter which one is negative, which one's positive. Of course, the magnitude of that vector is root 2, and so the second eigenvector here is just simply 1 over root 2, negative 1 over root 2, and that answers that question. So we move on. The next question says, which of the two principal components would be preferred if you only use one? Well, the one that you would prefer to use if you can only use one of the principal components would actually be u1, which, if you recall, was 1 over root 2, 1 over root 2. Okay, next question. What information does a PCA algorithm use to decide that one principal component is better than another? Well, it uses the eigenvalues. So whichever eigenvalue is largest is the, I guess, better principal component. And so here we just say the eigenvalues. And you can, if you're wondering why, you look at the next question. It says, from an optimization point of view, why do we prefer that one? We prefer the principal component that has the highest eigenvalue, x dot transpose x dot, because it captures the eigenvector associated with that captures the direction of greatest variance of the data. So in other words, if you want to really get an idea of the structure of your data and how maybe some data points kind of cluster with others while at the same time separating or being separated from other data points, then you would want to look at the direction of greatest variance. Okay, next question. Compute the vector projection of each of the original sample points, not the centered sample points, onto your preferred principal component. So by vector projection, we mean that the projected points are still in R2. Right? So you can think of all these points are, vectors pointing in R2 in some direction. So 0, 0 is just like literally at the origin. And then 0, 1 would be, along the y-axis. This one would be pointing along the x-axis, right? But if you projected those points, or rather those vectors, onto the line that u1 sort of, all multiples of u1, then, yeah, that's what they're looking for. And so to get a projection of a vector, so we want a projection onto u1. What we actually want is for each point, call it x sub I, we want its dot product with u1. And then we want to, so that's just sort of the magnitude or the length of the projection. And then since u1 is in a unit vector, we can just simply multiply by u1 here. And so this is just what we're doing for each one of these points. And so the projections, I don't know, I'm not going to necessarily call them anything. I'm just going to write it as a set. We have for the first one, the dot product of, and again, I'm calling this, x1, x2, and so on, right? The dot product of x1 here with u1. Well, u1, as a reminder here, u1 is this 1 over root 2, 1 over root 2 vector, but the dot product is just 0 times both of these, so 0. And so that's 0, and you zero out the vector, you're just going to get 0, 0 still. So, of course, you're at the origin, you're going to project on the origin because, well, it turns out that that vector passes through the origin. The next data point, x2, let's see. So you're going to dot 0 with that guy, or you take the product of 0 and that, so that's 0 plus 1 times 1 over root 2. Right? Well, it's just 1 over root 2. So your dot product is 1 over root 2 times this. Of course, 1 over root 2 times 0 is 0. And 1 over root 2, no, sorry, not times this, I apologize. Times u1, I apologize. So 1 over root 2 times 1 over root 2, well, that's a half. And again, we get the same point. So that's 1 half, 1 half. So this point gets projected onto the point 1 half, 1 half. And then the next point, it's the same thing. It's going to have the same dot product. Doesn't matter where the zeros are. You're going to get 1 over root 2. Of course, you're taking that dot product and multiplying by u1. So actually, you get the same exact point here. 1 half, 1 half. Okay. So that's x2 and x3. x4 gets projected to, let's see. So you got 1 times 1 over root 2 plus 2 times 1 over root 2. Well, that's just 1 plus 2 over root 2, or 3 over root 2. So you got 3 over root 2 times this. So you're just going to get in the first component 3 over root 2 times 1 over root 2 is just going to be 3 over 2. 3 over 2. Same thing for the second component, 3 over 2. Looking at x5, it's actually, again, going to give you the same exact dot product. And so we get the same exact projection. 3 halves, 3 halves. Finally, we have x6. You get 2 times 1 over root 2 plus 2 times 1 over root 2. Well, that's just 4 over root 2. When you multiply that by u1, you're going to get 4 over root 2 times 1 over root 2, or in other words, 4 over 2. Or in other words, just 2. You do the same thing for the second component, 2. And so these are the projections of your original vectors onto the line that goes through the principal component, so the principal direction. Okay, I hope you found that helpful. See you next time.